Hi everybody. Today I'd like to talk to you about our next problem, and our next problem happens to be a confidence interval. In fact, this confidence interval, we're going to have to try to decide what kind of confidence interval it is. So let's read the problem together. And remember, you can pause or stop this video at any point if you want to try the math yourself. That's totally fine. And if you have your graphing calculator ready, that'd be cool too. Okay, so it says researchers would like to know the number of fish that are being caught from a boat versus the number of fish being caught from the bank or the shore from a very large lake. The researchers have selected 12 random days from the fishing season, 200 days, and compared the number of total catches from all of the boats to the number of total catches from the bank. Using a 95% confidence interval, create a confidence interval that will approximate the mean of the difference. Okay, so we're going to try to catch something with an interval because that's what intervals do. And today we're going to try to catch the mean of the difference. And if you ask yourself, how did the fish answer? Do they answer with like yes or no, or do they answer with a number? They're answering with a number. They're answering with how many of them were caught that day, either from a boat or from the shore or the bank. And so if we look at that, we're looking at the number of fish from a boat versus number of fish from the bank or the shore, okay? And we have 12 random days, and we're comparing the boat and the shore. And so, you know, what would be a really good thing to use here, and it might be something that would have us do a matched pairs. And the reason why I say matched pairs is because ask yourself, should the boat and the bank be connected? For example, on day 4, there weren't a lot of fish being caught. 19 fish from the boats and 14 total fish from the bank. So the fish weren't really biting on that day, if that's a thing. But like on random day 6, the fish were really active, and it looks like a lot more were being caught off of boats than being caught off the bank. So should those two be connected? And I say yes, because each day you can compare if there are more fish active or less fish active. Like maybe, you know, the temperature had something to do with it, or the season had something to do with it, or something, right? So we're going to connect those together, and we're going to be looking at the difference. First, we're going to look at the difference between the boat and the bank, and then after that, we're going to find the mean of the difference. So that parameter is going to be based on the difference. So the first thing we're going to do is we're going to have to create a third list. So the list that we're really concentrating on is not the individual lists of how many were caught off the boat or the bank. It was the difference between the two. And I'm going to do boat minus bank. And I'm going to call it boat minus shore, because boat and bank still start both with B. So for example, day 1, random day 1, they were equal. So there was no difference between the number of fish being caught from the boat or from the shore. But on day 4, there's a difference of like 5. So I'm going to concentrate just on the difference. And by doing so, we have a parameter, and the parameter is going to be based on the true mean of the difference. So there's a little subscript d in my mu, so it says mu d is the true mean of the difference of total fish caught on any day from either a boat or the shore. And so notice my description has context to it, and it is the mean. And remember, we have matched pairs, and we also have two sample. A two sample would be the difference of means, but we don't have two means. We only have one mean, so we call it the mean of the difference, the one mean of the difference. So that's one of the major changes of using matched pairs. So next, I like to always indicate how I subtracted, because that often will make a difference to people, especially when you're looking at like a null and alternative hypothesis, if you expect the difference to be greater than 0 or less than 0. In this case, I'm doing a confidence interval, but I still like to tell people how I subtracted. So I subtracted boat minus shore. I like to put that somewhere in my problem so that it's obvious. All right, so let's talk a little bit about matched pairs intervals in general, just some tips and ideas about matched pairs. So first of all, we always want to catch a true parameter. That's what a confidence interval does. And then the way that we do that is an estimate plus or minus a margin of error. And a matched pairs interval is really just a t interval. That's all it is. It's just a specialized t interval. It's a t interval based on just the differences. So if you already know how to do a t interval, then you should easily be able to do a matched pairs interval. So again, one sample, and that sample is just list 3, is just the sample of the difference. And because it's only a t interval, then the degree of freedom is just n minus 1, super basic. And the formula is the same. So we have x bar plus or minus t star s over the square root of n. Now, a lot of people like to put little subscript d's all over the place, and you totally can. It really makes no difference to the formula. So if you want to call it x bar subscript d, you could, but it doesn't make any difference to the math. All right, so let's move on to the assumptions and conditions, and let's verify if this is legitimately a good problem to do. So what's the first assumption that we always make? And that is we have one independent sample. And I say the word one because if we were doing a 2 sample, we'd have 2 independent samples. In this case, we just have one, and that sample is just of the difference. And you can tell in the problem, they say that they had one sample of 12 random days, and that's exactly what we have here. So they selected the days without replacement, so let's make sure that we have that independence. So we're going to do n times 10 is less than big N, and we have 12 days times 10, which is 120, is less than 200 days. And so that checks out, and that seems reasonable. The next is our sample good? And so we have a random sample of days that's also given to us. So we're feeling very good about our one independent sample. The next thing we'd like is we would like an approximate normal distribution since we're using t. Now remember, we can go about this 3 ways. Now, you can choose any of the 3 ways, but sometimes there's only one option. So in this case, we're looking to see, is the original distribution given to us as approximately normal? No, nobody said anything about that shape. Or is our n size large enough, like greater than 30? We could use the central limit there. No, that's not given in this problem either. But what we do have in this problem is we have data. And so we're going to go ahead and we're going to graph the differences. So just of list 3, boat minus shore, number of fish. And what we're looking for is the shape of this graph. So notice the number of fish gives us some skewness but no outliers. And so it's reasonable to assume that the actual population distribution is going to be approximately normal, and that's fine. So moving on, we're going to go ahead and do some summary statistics on list 3. And we get the following pieces. So our x bar, our s, our n, and our degree of freedom is all given to us here. And we now can attach a t star to the level of confidence. Now, if you're using a graphing calculator, you're probably just going to let your calculator do all of this work for you. But if you want to remember how to find the t star, remember a confidence level is the middle percent confident. And that means from the very left, if we travel 95%, we have to travel through that little percent of tail, which is 0.025. And so that's a total travel distance of 0.975 from the left tail all the way to hit that upper critical value t star. And I use an inverse t on my calculator to find that. So it's 2.2 using a degree of freedom of 11. Putting all of that together, if I was going to do this longhand, I can throw it into my formula. And remember, it's fine not to write the formula in symbol form and just to plug in the values into the formula. That's more than appropriate. And so notice I get about 1.08 fish to about 3.58 fish. And so if I were to do this on my graphing calculator, I would go to tests. I would go to t interval. Remember, there's no matched pairs interval on your graphing calculator because a matched pairs interval is just a t interval. And I would select data since I have data and I'm using L3, and I'd put in 0.95. But if you don't, you can select stats and you can enter in the stats. So there's my confidence interval. But we all know that we're not finished until we write a nice conclusion. So again, carrying over my answer, those are my two interval values. And so the first thing you can say is something like, I'm 95% confident that the true mean of the difference for the number of fish caught from a boat compared to the shore is from 1.09 to 3.6 fish. So you could say it that way. Or I even like this way as well. Something like, there is a 95% level of confidence that a person will catch from 1.09 to 3.6 more fish fishing from a boat than fishing from the shore of this lake. Anyway, I hope this helped, and I'll see you next time.